Hi, welcome to this video. My name is Christoph Völker and I'm a researcher in a junior research group at BAM called Materials Characterization and Informatics for Sustainable Building Materials. And today we're going to talk about the exciting world of AI-driven materials design. In the first part, I want to give you some background and some motivation for you to find out who this could be for. In the second part, I will introduce our software tool SLAMD. In this hands-on session, you will understand how to use AI-driven materials design in the lab to design more sustainable and environmental friendly materials. Let's get going. Okay, so let's get started with data-driven materials design for cementitious materials. And you might be wondering, why do we need a new design approach? Let's have a look. The truth is, construction materials are in a major sustainability crisis. The production of cement alone amounts for 8% of man-made CO2 emissions. And the ecological question is thus far unresolved. You might think, why don't we just build everything made from wood? The problem is, we need to find a solution that works at scale. If we want to replace 20% of cementitious materials with wood, we would need to plant a forest 1.5 times the size of India. And we are already using more wood than we produce. Furthermore, 60% of all wastes come from the construction industry. This is a big number, but when you think about 50% of everything mankind produces is concrete, this number starts to make a lot of sense. The problem is that these materials are mostly sourced from primary resources, which are used in the construction process. And at the end of the lifetime, buildings are just being demolished and the waste ends up in landfills. So there's a huge circularity gap that requires closing. The thing is, waste is a material with unknown properties. And if we could enrich waste with information, we can transform waste into viable resources. So here's an undeniable truth. That is true for concrete, but also for many other materials. If we want to increase the performance in terms of circularity, CO2 efficiency, and cost efficiency, this comes at the price of complexity, which means resources are less and less pure, the material composition is getting more complex, and local supply chains make planning much harder. So this is how this complexity trade-off looks for concrete. If we want to reduce the ecological impact, the complexity of the formulation of the material increases. From initial optimizations with higher packing density of the aggregates, we are now moving to a world in which we replace the cementitious materials with supplements and also try to use secondary resources as aggregates. So this is the formulation complexity, but there is a second complexity that comes from the precursors themselves. If you look at this oxide diagram, you will notice that Portland cement has a very defined composition, whereas alternative materials such as waste slags, fly ashes, or natural puzzolans are much more scattered in their composition. This means that one day your waste slag could have a composition in this corner, and on the next day it could be here. But we can act on this complexity by combining various precursors with each other, and then find materials in this combined design space which fulfill the requirements we have. And this is where the AI approach comes in. The AI's purpose is to navigate towards these materials as quickly as possible and as effective as possible. But how does it work? The challenge lies in navigating these complexities. Previously, our approach has been to sample a representative set of formulations. Basically, take one formulation from each corner of the design space. The problem is that the whole concept of representative data does not exist for complex problems. This has to do with the weird geometry of high-dimensional spaces. So it is not a problem of our ignorance or a problem that we could solve with collecting more data. It is a fundamental problem of complex systems, such as sustainable materials. The AI approach, on the other hand, works differently. Here, we try to navigate the complexity, which means we start out at a given point and then systematically work ourselves towards formulations that work and meet our requirements. This way, we can ignore a huge part of the design space and only focus on the materials that are viable for our purposes. So AI-driven materials design navigates towards the target in short feedback cycles. You collect data, you train a model, which shows you the next data point to collect. And this updated cycle helps you to navigate quickly towards your target. Whereas in screening, you collect your representative data sample, and if you're not able to find a good material, what are you going to do in the next round? You could try to enhance the data set, but there's no targeted way to reach your specification. How do we know that it works? Well, we measured it. In a large-scale case study, we conducted more than 10,000 simulated design runs in order to measure the time an AI-driven approach requires to find predefined materials. Here's how it works. Basically, you collect data from the literature, so this is real lab data, data that scientists have reported. And then within this data set, specify a material of interest, for instance, a high-performance material. We then initialize the AI with a randomly selected training data set and count how many updates the AI requires in order to find the specified materials. And we don't just do this once, we do this over multiple runs with randomized initial conditions. And this gives us a distribution of the development time required of the AI approach to find these specified materials. And here you could analyze, for instance, the mean time, or you could even analyze the 90% success probability, which means that in 90% of the cases, the material was even faster discovered. And this measure is very robust. It's a lower bound measure of the performance. And we did this over 9 large data sets in more than 10,000 experiments. And we measured an acceleration of up to 40 times compared to screening the whole data. So 40 times, this is a really big number. You can think of it as being 40 times more efficient than not using AI. Another benchmark that we looked at is random sampling, so basically relying on luck. This is a common benchmark, and even compared to this benchmark, which is more efficient than, of course, screening the full multitude of formulations, even here we have an acceleration of 10 times. So AI is 10 times more efficient than luck. But what do these numbers mean? 10 times, 40 times, these are big numbers. Does it mean that we're just ready in the lab 10 times faster? Well, actually, we aim to use this higher efficiency to increase the performance. In other words, we can now investigate materials that are 10 times more complex than previously. And to do this, we developed a design software. The design software is called SLAMD. It's an open source software. It's platform independent. You can access it worldwide on any device. The access is free, and you just have to follow this link. And this software combines a digital lab twin. Think of it as a tool to create these caves full of formulations, and an AI optimization tool. So basically a tool that helps you navigate this cave. So in the next section, let's have a look at a hands-on example on how to design sustainable materials with our software tool. So welcome back everybody to the second part of this video, which is a hands-on session with our materials design tool SLAMD. Let's find out how this all works and how to get started with this tool. Basically, you just have to visit this URL, slamd-demo.herokuapp.com, and you'll find this home screen. And this home screen provides you with everything you need to get started, including a user manual, which contains a step-by-step guide through this software tool. Additionally, there's a link to the GitHub repository, our code repository, in which you find the source code to download and to install locally. There's a README that talks you through the installation of this app if you want to run it on a local server or on a local machine. And there's a section with resources that contain all the articles or data sets that we made available for you to get started with this app. So this home screen shows our workflow. It is divided into two sections. There's the digital lab, which helps you to create this cave, so to say, so the multitude of different formulations that are feasible. And then there is this AI optimization tool, which helps you to navigate through the cave and find materials that match exactly your requirements. So let's start with some housekeeping. If you are using this app and you finalize your work for the day, you can save your session by simply clicking this link. If you want to continue to work on your previous session, you can upload the session and just work on your previous project. If you don't save the session, all data will be lost with the end of the session, so basically after some time of inactivity. I already pointed out the user manual, but when you go through the software, you will note that there are many of these gray boxes which explain exactly what is expected from you. So let's get started. And we are going to start with the digital lab. So the workflow here is first create all the base materials in the digital twin. So basically all the resources you have at hand. You have the opportunity to mix resources, blending powders or creating activator liquids. And then at the end, with a few mouse clicks, you can create hundreds and thousands of formulations. So let's start with the base materials. The workflow is pretty simple. The first thing you have to do is give your resources a name. You can start with, for instance, a cement powder, right? Type in the name of the material, then select the material type. There's a couple of options. You can choose a powder, a liquid, aggregates, admixtures, a process, or add something custom. Depending on which material you've selected, you can specify properties. There are shared properties, such as the CO2 footprint of the material, which you can just type in, or the costs, mix that up, so 450 kg per ton, and 80 euros per ton for a cement powder. But there are also specific properties, such as the composition. And for powders, we have proposed for you a number of oxides and structural composition, such as the fineness of the powder. But if there is something missing that you deem important for your experiments, you can always add custom properties, such as, let's say, color. And the powder is gray. Okay, maybe you have something that makes a bit more sense than the color. Then you can just click submit and the material will appear at the bottom in this list. If you want to edit the material, you can always click on this pen and go back to the fields and enter compositional information or information that you forgot previously or that you now want to edit because, for instance, there was a price drop. Okay, so let's upload a session that I've previously created. And in this session, you see we now have multiple materials. There is an admixture, we have different kinds of aggregates, water constituents for the activator liquid, powders, and so forth. And with these materials, we can now go on in the workflow. Let's delete cement. We're going to use these materials instead. And what you see is that all of these materials have specified information. For instance, these coarse aggregates, they have a composition. There's a cost attached to these materials. And we will use these information later on in the design process. Okay, moving on to the next step, which is blending materials. So you might want to use various materials, but you're not, or you want to combine various materials, but it might not be obvious which weight ratio is the best. So what you can do is create a multitude of different weight ratios by just filling out this form. For instance, you could blend fly ash and ground granulated blast furnace slag and create a blended powder, which I would call blend FAGGBFS. Again, there's this gray info box that gives you all the necessary instructions. So how does it work? Instead of specifying every blend individually, we can here specify a range of blends going from, for instance, 50 to 70 in steps of 10%. So basically, you will create a 50% 50-50 blend between fly ash and slag, a 60-40% blend, and a 70-30% blend. And you only have to specify these three numbers, and it calculates for you the blending ratios automatically. You can also edit them or delete individual blending ratios if you don't require them. And in this way, you can create blends of materials, and the blending occurs to a weighted average, and the weight is according to the weight of the material. So it's a mass-based material model. And what you see here are now the blended materials, 50-50, 60-40, and 70-30, with the shared properties according to the weighted average of these two materials. Okay, moving on from blended base materials, blended materials, to the formulations. You have the option to specify either a concrete formulation or a binder formulation. The difference is that in concrete it is required to choose aggregates, whereas in a binder it's optional. So you can also create a mortar paste, for instance, here. So let's create concrete formulations. And you don't have to create individual formulations. This tool will just help you to create a whole bunch of formulations with just a few clicks. For instance, by selecting the powders you want to use. In this case, let's just use the blended powders, the liquids, which is a blend of pure water, sodium hydroxide, and silicate to create an activator liquid, and the blended aggregates, as well as a superplasticizer, and in this case, heat curing and ambient curing as processes. The material model in the background of SLAMD is weight-based at the moment. We are planning to introduce a density-based material model later this year, but thus far you have to specify the weight of the formulation. So let's just say 2,400 kg, which is roughly a cubic meter. Let's give the dataset a name and move on to specify the weight fractions. We start by specifying the weight fractions of the powder, again by just providing increments, minimum to maximum, and the increment. We can specify various water to cement ratios or water to powder ratios, again by specifying a range of parameters, 0.45 to, let's say, 0.6. And we can also add super plasticizer, let's say, in 5 kilo steps from 10 kilo to 15 kilos. Okay, so by typing in these numbers, we can create all the weight fractions of the formulations, which are shown here. It is possible to edit these weight fractions or to delete individual weight fractions. And now, based on these automatically calculated weight fractions and the selected materials on the top, you can create your materials design space by simply clicking the green button. And now we have a large table consisting of many, many different compositions and materials, which is just based on the form we filled out above. So this is a super simple way to create the search space in which there might be the ideal material candidate that we don't know yet. How to find it? If we want to work with this data set, first what we have to do is to submit it. Now it will occur in our next window, the discovery window. Let's talk about this in the next part. Okay, moving on to the next section, the discovery module. So this is where things get exciting because we finally start optimizing our material. On this page, you already see the dataset we've just created in the digital lab. For the sake of this tutorial, I prepared a second dataset that I can just upload using this CSV file upload dialog. So technically, you don't need to use the digital lab to create a dataset. You can upload any CSV data file. So let's use this example, select it, upload dataset. Here we go, it appears in this list. Let's have a look at the data. We can delete the data, select the data for the optimization problem. We can add targets to our dataset and download the dataset. Let's have a look at this add target dialog. So once we created the dataset in the digital lab, we now need to add targets. So we need to add labels for the machine learning model to be able to make predictions. We can either select a column, a target column from this list, but if there is no target column available, for instance in the initial round, you can give it a name using this field, for instance compressive strength, 28 days in megapascal, and then simply click add target. And now we can add this value for the various formulations we have at hand. So let's say we go to the lab and test formulation 20 to 25. We can enter here the measured values 24, 34, 56. So these are just dummy numbers, right? But this is how it would look. So with this data at hand, you can either scroll all the way down and click on Save Targets or just press Enter. And then you'll have these new labels available in your data set. Okay, moving on to the optimization. The main objective here is to set the optimization problem, to initialize it. And for this, we just click on this blue data set. And then we first have to select the material's input data. So basically, all the columns that describe our material. So here you find again all the info you just entered in the digital lab twin. And you can select it, in this case, up until temperature. And then you have two further columns. One to select the target. So this is the prediction target, something that requires prediction. In our case, let's select the 28-day lab strength. And a third row for a priori information. So this is information which is available a priori, for instance, the cost of the mix or the CO2 footprint of the mix, which is just a combination of the costs or the CO2 footprint of the constituents of the mix. So no prediction required. You can just straightforward calculate this. And this is, for instance, something that the digital lab does for you. So you could select this as an optimization target as well. But let's just start with optimizing the mechanical property, the compressive strength of the concrete. Once you selected your target, you can choose between maximize and minimize. Of course, we want to maximize the strength. And then all that's left is click the green button to make a prediction. And the prediction appears below in terms of this plot, where you see the predicted value for all the formulations and an estimated utility. So this estimated utility is an abstract measure which just correlates your scenario, your design scenario, in our case, maximize the strength, using the predictions with this utility value. And in our case, we want to maximize just the strength, so the highest predicted strength gets the highest utility, and it's here colored in yellow. So this makes it super straightforward to select your sample. Let me give you another example. Let's just say we want a material with 47 megapascal. This is our target strength. Everything above does not add utility. Let's add this threshold here. And now we can see that all materials that have a higher strength than 47 megapascal now have the same utility. Yeah? So this utility measure lets you specify arbitrary design scenarios and specify exactly your requirements, and you'll end up with a simple selection metric, the utility, which makes it super easy for you to select the right design. For instance, let's optimize compressive strength. We want to maximize this, and CO2 footprint, of course, we want to minimize. Now we run the experiment again, and now you see a plot of CO2 footprint versus compressive strength for all the materials in our design space. And the materials that have a particular high strength and a low CO2 footprint have the highest calculated utility. Okay, so this is the way you can specify your different design targets. For the sake of this experiment, let's keep it simple. Let's just max out the compressive strength. Okay, but there's something else that I have not talked about yet, and this is the curiosity. And this is basically something that lets you strategically decide which materials to favor over others. If you set the curiosity towards explore, it means that materials with a higher predicted uncertainty are prioritized before materials with a lower uncertainty. So now we are not only optimizing towards the highest strength, but we add to this the uncertainty of this strength, so the prediction uncertainty. So instead of the utility being aligned with the predicted value, we now see the utility being aligned with the uncertainty of this prediction. Okay? So this way you can strategically select materials that your algorithm or your prediction algorithm is predicting high values, but also high uncertainties. Okay, to make a selection, you could either refer to this table, which organizes all your formulations in this design space and sorts them based on the estimated utility, or you could use this plot of the input space, which gives you basically a map of your materials. So what we see here now are 240 points, because our design space contains 240 different formulations. And we see a bunch of crosses, which are materials that have already been validated in the lab. So somebody already went to the lab and made a huge effort in order to collect a lot of training data. But what you can also see are all these other materials that are currently untested. So what do we have here? These are 3 clouds, so 3-point clouds, which refer to 3 different materials, so different fly ash, slag, blends. We also have 4 lines, which refer to 4 different water-cement ratios, and then 10 different variations of this cement ratio with different powder content, okay? And then there is one version with ambient curing and one version with heat curing. So basically here you have a nice overview over all the variations that would be possible, but which previously we haven't considered in the lab because of the tight lab budget. Imagine testing 240 formulations. This is so much work, but with this tool we can now select effectively data points that have the highest information content. So by going with your cursor over these points, you see the row number, which refers to this table, right? So basically you can see which materials are being preferred here. Yeah? And let's say if the highest utility was here, you wouldn't need to select this. You could choose just within different point clouds the materials with the highest utility, which offer you, for instance, the highest insight. Okay, but let's just select the first 5. 1, 2, 5, 3, 4. Yeah, so 1, 2, 3, 4, 5. These materials for validation. How does it work? We could now go to the lab and create these mixes that are described here. The predicted strength is shown here, so the model does not know too much at the moment, so the predicted strength is very similar for these 5 first formulations. Okay, let's see how they play out in the real world. So we have formulation 137, 57, 177, 17, and 217. So let's see if I can remember them. To do this, we would now go to the lab, do all the testing, right? Once we're done, we go back to this dialog, select the compressive strength as the target. In our case, this is the target, the lab validation. Let's deselect this. And this is data from literature, so we already know the ground truth. Let's just enter the inputs, the strengths that have been previously collected in the lab. So formulation 17 resulted in 60 megapascal. I think the next one was 57. Oh, 64, so this is a high strength material. Then we had 117, I believe. So this is not so high strength. Was it 147? And 207, I believe. Okay. Oh, 28.3. So this is a very low strength. The model previously calculated the same strengths for all these materials. Let's add this information and look at how the prediction of the remaining materials change. So just an observation here, we already validated materials with up to 65 megapascals or just below 65 megapascals. So we already found in just one round very high performing materials. Let's have a look at our map again and see how this changes the landscape. Oh, and the landscape changed dramatically. Previously, we had more or less equal distribution of good-looking materials on all these 3 point clouds. This is no longer the case. Here we have our initial training data set, and we see that these materials are all in the purple region. We see that this material system has a very low estimated utility, so basically we can ignore it for future investigations and instead focus on this material here, which, let's have a look, seems to be a 50-50 fly ash slag mixture with heat curing. So now the task of investigating 240 formulations has been Simplified, we now know that we should concentrate on materials with heat curing and with 50-50 slag fly ash mix. And now the task is to find the best fine-tuned material amongst these. We could do this by just iterating 1 or 2 more times to find the ideal candidate. But I hope this example gives you an insight on how AI-driven materials design is executed and what is the advantage. So let me quickly summarize. Basically, we can create scenarios, or we can create optimization scenarios that also exploit a priori information. We can take into account CO2 footprints and so forth, and thus find more sustainable materials. It's very straightforward to specify different design targets. We can use a prediction model. We can use the uncertainty of the prediction model in order to find most informative materials to validate in the lab. We can use all these data dashboards that give us a very nice bird's eye perspective on our design problem to make strategic decisions. These decisions can take into account the predictions of the machine learning model, but you also always have the opportunity to make your own decisions and to prioritize just using these data dashboards to give you an overview. Then we have these nice tables that summarize for us materials with high utility, so with a high expected performance. And yes, after we've finished a design campaign, we can also download the predictions and then have a nice Excel table. So I hope this was interesting to you and that this resource is valuable to you. Please feel free to reach out to us. You'll find our homepage at the bottom of the landing page. And yeah, thank you so much for your attention.